The carbonyl, a carbon double bonded to oxygen, makes the key functional unit of a wide range of different functional groups. Specifically, our aldehydes and ketones, which contain just our carbonyl and then carbons and hydrogens, but then later we'll look at carboxylic acids, amides, esters, and other carboxylic acid derivatives that all use this shared carbonyl functional group unit. Aldehydes and ketones are our simplest functional group that include this carbonyl unit. Ketone contains our carbonyl attached to two carbon-based chains on either side. Our aldehyde is similar, but with a hydrogen, or perhaps two hydrogens, attached to that carbonyl instead of our carbons. Aldehydes and ketones are our two simplest carbonyl-based functional groups. Our aldehydes have our carbonyl with at least one and perhaps two hydrogens bonded to that carbonyl. Our ketones have only carbons bonded to that central carbonyl. So essentially we can look at our aldehyde as the less substituted form of our carbonyl functional group, whereas our ketone is the more substituted form with our carbons on either side. As with our other functional groups, we want to look at the naming properties and reactivity of our ketones and aldehydes so we can get a better idea of how these functional groups affect our molecules and then how they might behave in biological systems. As always, when we have a new functional group, we need a new suffix to indicate the presence of that functional group. For ketones, we're going to use the ONE ending. So for a given ketone, we first need to count out our number of carbons. So in this case we have 1, 2, 3, 4, 5, 6. So that makes this a hexanone. Again, using that ONE ending to indicate our ketone here. Now, of course, our ketone can be anywhere in our carbon chain since it's between two carbons. So we also need to have a number here to indicate where our ketone is. Now, of course, as always, we want to give the lowest number possible to our ketone functional group. So if we number from the right side, that puts us as a 2 here, and this would be 2-hexanone. For an aldehyde, we don't have to include a number because our aldehyde will always be at the end of a carbon chain. Right? So we always have a hydrogen attached to our aldehyde there. And then, of course, our carbon chain would continue from there. In this case, so our longest carbon chain needs to include our aldehyde. We go 1, 2, 3, 4, 5, 6. So this would be hexanal. Of course, our counting comes from the first carbon with our aldehyde here. And so this would be then a ethyl branch with 2 carbons coming off our third position. So this would be 3-ethyl hexanal. Now, of course, whenever we introduce new functional groups, we also need to understand how to prioritize naming these functional groups versus other functional groups. So our aldehydes are going to take first priority over our ketones, which will take priority over alcohols. And of course, alcohols, as we've seen before, take priority over our other functional groups like alkynes, alkenes, alkyl halides, etc. So let's say we have a molecule that combines alcohols, ketones, and aldehydes. Okay, so here's our new compound. Now, of course, we always want to start our carbon chain at the aldehyde. It takes priority over our other functional groups here, and it always will end up with being the first carbon. So that's carbon 1, 2, 3. So 3 is where our ketone is. 4, and then of course we want our parent chain to include the alcohol. So this is going to be our 6th carbon up here. So this then ends up being a hexanal again. So it's another hexanol derivative similar to the structure that we showed here. And then we have our ketone at the third position. To indicate a ketone here, we're going to use the oxo prefix. So this is going to be 3-oxohexanol. And then of course at the fifth position we have a methyl group. So that's going to be 5-methyl. And at the sixth position we have an alcohol. We'll indicate this as 6-hydroxy. So the full name is 6-hydroxy, 5-methyl, 3-oxohexanol. For our ketones, we do occasionally see a functional base nomenclature as well, similar to what we've seen previously for ethers. So in this case, we would separate out our molecule as basically two different alkane chains on either side of our ketone. So we can look at our ketone right here, and then name each of these on either side. So this would be methyl, this would be butyl with 4 carbons, and this would end up being a butyl methyl ketone. So you do see this naming system occasionally, such as the methyl ethyl ketone peroxide that we use in our lab, but the substituted nomenclature system tends to be preferred for our ketones and our aldehydes. In order to get a better idea of our reactivity and the behavior of our ketones and aldehydes, we need to take a closer look at the structure. Now, of course, since we have a carbon double bonded to an oxygen, that means we're going to be sp2 hybridized. So our carbon is going to have a p orbital and our sp2 orbitals. We use one of our sp2 orbitals to bond with our oxygen. Our oxygen is also going to have a p orbitals so that we can overlap and form that pi bond. Right, so we get our typical pi and sigma bond between our carbon and our oxygen. Of course, our oxygen will have lone pairs and its other two sp2 orbitals, whereas our carbon will have bonds to either other carbons over here for our ketone or hydrogens and or carbons for our aldehyde. Now, since our oxygen, of course, is much more electronegative than our carbon, this bond is going to be polarized towards our oxygen, right? So we end up with that partial negative charge in our oxygen and the partial positive charge in our carbon. Now, since there's 4 electrons between our carbon and our oxygen with this double bond, this bond has an even larger dipole than a carbon-oxygen single bond. So there's actually a large difference in that electron distribution between these two atoms, which creates a rather significant dipole. Now, of course, a dipole gives us one of our moderate strength intermolecular interactions. So that will give our ketones and aldehydes higher boiling points compared to things like ethers or alkanes. However, we don't have any hydrogen bond donors here. Our ketones and aldehydes aren't protic, so we're not going to have as high of boiling points as alcohols. So in terms of our boiling points and melting points, we can say that our alcohols will be at the top. Then we have our ketones and aldehydes. And then below that tend to be our ethers. And below that are our hydrocarbon functional groups like the alkanes, alkenes, and alkynes. Of course, all of these are relative and depend on the number of carbons that we have. Ethers and hydrocarbons tend to be pretty close. Ketones and aldehydes just slightly above that. Alcohols, of course, are significantly higher due to that hydrogen bonding. Again, as with our ethers, we will have decent water solubility though due to the hydrogen bond acceptor of our oxygen. Right? So when we have our water molecules, we've got our polarized bonds towards our oxygen, and so we're going to have our partial positive hydrogens here that can then hydrogen bond with the partial negative oxygen of our ketone or our aldehyde. And so we can end up with pretty good water solubility, at least for our smaller ketones and aldehydes. So overall, our ketones and aldehydes are kind of between ethers and alcohols in terms of their properties, right? So they have decent water solubility, but not as good as alcohols. They have reasonable boiling points and melting points, but again, not as high as those alcohols. But they're also higher than ethers in both solubility and boiling points and melting points, because we have the stronger dipole as well as that same hydrogen bond acceptor ability that allows us to hydrogen bond with our water molecules. The reactivity of our ketones and aldehydes is going to be based on primarily the strong dipole here between our carbon and our oxygen. Right? Again, I mentioned that the overall strength of this dipole is affecting our physical properties, but of course that also determines what our nucleophilic and electrophilic sites are in these carbonyl-based functional groups. So our oxygen is a good nucleophile. As we're pulling that excess electron density towards our oxygen, whereas our carbon, because its bond is highly polarized, is going to be a great electrophile. Now, of course, since we have a double bond here as well, so that means that we do have a lot of electrons here in general. So we can take those electrons to react as a nucleophile. Those electrons are kind of going to be more centered around our oxygen. So our oxygen will react, it can act as a base and pick up hydrogens there, whereas our carbon is always going to be the focus of attacks from other nucleophiles. So you get that really strong electrophile, and so a lot of our reactions to our carbonyls are going to be nucleophilic addition reactions, where we're going to be attacking that carbon with our incoming nucleophile, and then our oxygen will react at the same time, and so we'll usually end up adding on a bond to our oxygen and a bond to our carbon, and we'll create an overall addition reaction with adding those two groups on either side of our double bond. So in some ways it'll look a little bit like alkenes, right, where with alkenes we're always adding on two things on either side of the double bond. But in this case it's going to be a little bit more nucleophile focused, where our nucleophile is always going to go to the carbon, and then our oxygen is usually going to pick up generally an electrophilic hydrogen at the same time as the nucleophile is attacking our carbon. We'll take a deeper look at the variety of nucleophilic addition reactions with our ketones and aldehydes in future lectures.